Welcome to all of you to International Symposium on Parameterized and Exact Computation, IPEC 2010. Previously, it was known as International Workshop on Parameterized and Exact Computation, but from this year onwards, we are going to call it IPEC and replace workshop to symposium because the generality of the conference has increased. And for today, we are going to start our first day with an invited talk by Professor Fedor Fomin. He did his PhD from St. Petersburg State University, Russia in '99. And after that, he did his postdocs in Chile, Charles University, and University of Paderborn. And since 2002, he's a professor at University of Bergen. His research interest mainly includes graph algorithms, complexity, and few things, which the most important things or fundamental contribution which he has done in last 10 years, according to me, is two things which I remember. One is this whole concept of bidimensionality, which led to complete generalization of lots of nice algorithms on graph minors and things like that. And then another in the area of exact exponential time algorithms with this introduction of measure and conquer, which led to many, many simple algorithms and good analysis. For some of you who were already here have heard about it. And among others, he's also involved in professional life. He has currently in the editorial board of SAM Journal of Discrete Maths, and he has been on program committee of several conferences like SODA and ICALP and other things. And recently, he's also been granted a very prestigious ERC Advanced Grant in Europe, and now I call Fedor Fomin to deliver his lecture on protrusions and its application in graph algorithms.
Thank you very much, Takit. And it's also a great pleasure to be here, and I enjoy being here. It's a very great thing. Yes. So it took some time for me to realize what I want to talk at this invited talk. And I started searching inspiration in the previous IPEC or IFPEC talks. So if you browse, there's a subset of invited speakers for IPEC. And I was looking what these people were speaking about. And so Mike Fellows in 2006, he gave a talk which was called The Lost Continent of Polynomial Time Preprocessing and Kernelization. Right? So that was in 2006. In 2008, my attention drew two invited talks. So the first talk was by Eric Demesne, who was speaking about algorithmic graph minors and bidimensionality. And also there was Stefan Kreutzer, who was giving a talk on algorithmic meta theorems. Okay, so the next, still IFPEC, Hans Badlander, was speaking about, in 2009, about kernelization, new upper and lower bound techniques for kernelization, right? And then I was thinking, well, do I really have anything choice, or should I start something new? And then finally I realized maybe I shouldn't tell you anything new. I just maybe should give an overview of previous talks. Or other things I was thinking, if I have any choice in my selection of the topics. And finally I realized that probably not, so I should speak again about kernelization, bidimensionality and algorithmic meta-theorems. So that was my, so so the choice we make in our life is not our choice, right? It's somehow it's influenced by what happened before us. So that was, so here I cannot say anything new. Okay, so basically what are the, but mostly I will be speaking about algorithmic meta-theorems for kernelizations, and bidimensionality will be a connecting link of these two things. So what is meta-theorems? So meta-theorems are quite a general type of statements, and these things which discover very deep relations between logic and combinatorial structures. So the famous examples of such meta-theorems, for example, is the Courcelli theorem, which say that every problem definable emanating second-order logic can be decided in linear time on graphs of bounded trivets. So it describes a huge class of problems in terms of some logic. And then there's also combinatorial restrictions in graphs of bounded trivets. When you combine two things, you have an amazing wide class of problems and results. So there are, so of course, it's not the only one theorem. For another example I can give, so like there's a Frick and Grohe first-order model checking admits linear FPT algorithms on planar graphs. And there are much more this type of results. So there are quite nice also survey of Martin Grohe and also of Stefan Kreutzer on algorithmic meta-theorems. So we discussed the relations of logic and algorithms. Yes, so the other area, so what I want to relate in this talk, so I want to relate meta-theorems and kernelization. So what is a kernelization? Well, that's the theory how to get a kernel out of something, right? So this is an informal definition of kernelization, a little bit more formal definition of kernelization. So what we want in kernelization. So kernelization algorithm is a polynomial time transformation that transforms any parameterized instance to an equivalent instance of the same problem with size and parameter bounded by a function of the parameter. So this is a more formal definition. And finally, so just let me be precise. So I just want to give so because it's an important notion, and then I will be speaking about kernels all the time. So I want just to be sure that we understand each other, right? So this is the formal. So let me just that will be probably the most technical definition in this talk. So just let us pass through it, and then we go. Okay. So once again, so what is a kernelization algorithm? I am speaking about parameterized problems. So every problem is given to me as a string and plus a parameter, right? And then what I'm doing, so if I have a parameterized problem, the algorithm works in polynomial time, and then it gives me another instance of the same parameterized problem, right? And the condition on this instance is that, well, if I have solution, so this is a input string, and this is the parameter. If this is solution of my problem, then the changed instance is also solution, or also belongs to my language. So that's the first condition. And the second condition is the also important one, that both the input length, so the size of the change problem and also the parameter, they also bound it as a function f of k. And then I use this kind of jargon. I would say that the size of the kernel is basically this function f of k. And also should be some computable function, but also there is a big distinction, the important distinction. I think that if this function is polynomial, then we say that the kernel is polynomial. So kernel can be of exponential size and can be of polynomial size. And just to give an example, so probably the most classical example is example of with vertex cover. So vertex cover of a graph is a set of vertices such that every h has at least one endpoint in this set. So if we look at the parameterized problem, so what we have, so the input size is the number of vertices plus the number of edges in the graph, and the parameter k is the size of vertex cover. This is the parameterized instance of vertex cover. And basically, so why vertex cover has a polynomial kernel? Well, if you write down vertex cover as an integer linear program, so we just want to minimize the amount of vertices subject that every h is covered at least once by every vertex. This is one condition. And if you take linear programming relaxation of this integer program, then it's a very classical result from 1970s of Nemhauser and Trotter that LP relaxation of this integer program has a super optimal half integer solution. And super optimal solutions means that if I take the sets of all vertices or variables which have a non-zero value, then this will be a superset of optimal solution. And then also it's half integer, so the only values are 0, 1/2, and 1. And then, so as a corollary of this result, it follows almost immediately that vertex cover has a kernel of size k square, right? Why? Because by Neuhauser-Trotter, if I take this LP relaxation of vertex cover, and I just take all vertices or all variables which got non-zero values, I will get a graph on at most 2k vertices, right? The graph has at most 2k vertices, but the size this graph has a vertex cover of size k if and only if the original graph has vertex cover of size at most k, right? So the number of vertices in this graph 2k, so which means that the number of vertices is at most 4k square, which is big O of k square, right? So the size of this kernel is k square. This is a quadratic kernel. So there are much more problems which have polynomial kernels. So another example, for example, is a feedback vertex set. Here the kernel is less trivial, so it requires some work to get this kernel of size k square. But also, so that's a quite nice example of another problem having polynomial kernels. And then you ask, well, if we have, is it true that every parameterized problem has a kernel? Of course, the answer is no, and there is a very deep and intimate relations of parameterized complexity and kernelization. So basically, roughly speaking, the problem is FPT if and only if it has a kernel, right? So it means that so there are problems which do not have kernel at all. Let's for example, like a k-dominating set, which doesn't have a kernel because otherwise FPT will be equal to W2, which is a strange thing if it occurs. And then so for a long time there was that was the only results people knew about kernels. But then also it appeared that it's quite also interesting to distinguish which problems have a polynomial kernel and which problems don't have polynomial kernels. And quite recently there appears also the complexity theory or the tools which proven lower bounds for kernelization, like Bodlander, Downey, Fellows, and Hermelin in 2000. So there was an Eichel paper 2007, I think. So they proved that there are several problems which do not have polynomial kernel, but still have still a fixed parameter tractable. So for example, the k-path problem. So the problem, I'm given a graph and I ask if there is a path of length at least k. So k is a parameter here. So for example, this problem, it's quite easy to show that this problem has a kernel of size 2k. But this problem doesn't have a polynomial kernel unless something strange happened in complexity theory. So, and as far as we start to distinguish problems, or we start to be able to distinguish the complexity or finding of kernels, if you have polynomial kernel or not, the industry start working, right? We have already complexity tools. It's time also to develop algorithmic tools to understand which problems really can be solved or reduced faster. Yes, and actually what is really also become quite interesting and quite funny, and this is what really start making things different from usual polynomial time algorithms. There are now tools which are able to distinguish problems or we're able to estimate up to some assumption in complexity theory the polynomial sizes of kernels. Just this thing is very exceptional in terms of polynomial time algorithm, because just, for example, can you prove with any assumption that you cannot find a triangle in a graph in running time, in linear running time, right? Of course, people don't believe in that, but try to make any assumption from complexity theory to plug it and to prove such type of things. I don't know any type of results. Or take matrix multiplication, right? Can you prove any lower bounds in terms of complexity theory on the running time of matrix multiplication, right? But for kernels, surprisingly, it's possible. For example, so there was a result of Dell and Mecklebeck, so showing, for example, that k vertex cover has a kernel of size k square, right? No, this is known. And also, but they show that the vertex cover doesn't have a kernel of size k power 2 minus epsilon for any epsilon, unless polynomial time hierarchy collapses to the third level, whatever it means, something very unlikely. So this somehow, at least to me, that was a quite surprising result. It shows really that it's something different than from normal polynomial time algorithms. Okay. So far, now there are quite many kernelization results, algorithm results. So also there are quite a lot of lower bounds, but still somehow what is really missing in this area? So there is no, what I would say, they're missing big hammers. What I mean by big hammer, so if you start thinking about approximation algorithms, right, there is a big hammer linear programming. Even bigger hammer semi-definite programming, right? So a lot of things. If you speak about polynomial time algorithms, there is also, so if you have a polynomial time algorithm, look for some minimax theorem, right? So basically everything is around matching for polynomial time algorithms, right? Well, I'm exaggerating. The same for parameterized complexity, right? So there is also powerful tools there. But for kernelization, so far, there's not so much thinking. And of course, maybe this is because of our lack of understanding what is the real nature of kernelization, what makes a problem to have a polynomial kernel. And in this talk, I want to speak about this type of general results. So the results which give some explanations why many types or many different types of parameterized problems have polynomial and sometimes even linear kernels. So that's what I want to talk today. And the main tool for obtaining this type of results, this is the protrusion. So what is I will give a formal definition of protrusion in a few seconds, but what is informally protrusion is the following thing. I have a graph, and then if I can take a piece of this graph, and this piece can be very large, but the property of this piece is that it communicates to the remaining part of the graph via a constant number of vertices, and also that the trivius of this piece is also bounded by some constant. So this is my objective protrusion. And why these tools, I will try to convince you that this is a quite interesting tool to obtaining this type of general results. And basically, from my perspective, or from my point of view, so protrusions for kernelization, they play the role of triviets in parameterized algorithms. So this is something. Okay, so the formal definition of the protrusion. And this is the main tool of this talk. So this is so what is once again protrusion? I have a graph, and then I have, if I have a vertex subset in the graph, I use this partial of G sign to denote the set of vertices in a graph S. So the neighborhood of the vertex set. So that's the vertices which have neighbors outside of the set. And then the definition of the protrusion is that I have a set X vertex set. I call it a protrusion if the graph induced by this set has a constant triviet. That's one property. And the second, the border of this set is also constant. For example, so the simplest example of protrusion is if I have just vertex of degree 1 hanging in a graph. This is protrusion, right? Because this one vertex has triviets 0, constant, and also it's communicated to the remaining graph also via one vertex, right? So this is yes. And why and how protrusions work in the graph? So the idea with protrusion is the following. So if I have a graph and I have a protrusion which is quite large, then what is possible, and so to do, it's possible to replace this protrusion, to shrink it, by equivalent instance, but of smaller size. So the communication of the protrusion to the remaining graph, it keeps the same, it's the same border, but I'm able to shrink the protrusion, and then what happens if I'm able to do this operation many times? Then basically this is sorry, I come back. Yes. So then basically this is the main idea. So if I have a big protrusion, I'm able to shrink it, and then again I look in my graph. If I have again large protrusion, I'm shrink it, and finally I end up with a graph which doesn't have a large protrusion. And then if my graph doesn't have a large protrusion, I'm also able to argue that, well, the size of the graph is bounded as a function of k, which means that I have a kernel of nice size. So this is the idea. Yes, and basically all techniques which work for protrusion, they use exactly the same. So all arguments are the same. So if I have we always need kind of combinatorial results, and the combinatorial results are of the following type. So if I have a yes large instance of my problem, then this large instance should have a protrusion. That will be, so the only combinatorial result we always prove. Okay. Yes, and as far as we're able to establish this type of combinatorial results, we have a kernel, right? Because once again, we apply this type of arguments. If the instance of my graph, if the yes instance of my graph is very large, I know there should be a protrusion. I find the protrusion, I reduce the size of the instance, right? I do it again and again and again, and as if I'm not able to find protrusion, either it means that I have a no instance, or the size of the graph is small. That's so basically so everything is just how to find the right protrusion in the graph. Yes, so I should say also a few words more formally how protrusions work, or how what do I mean that I replace one big protrusion by the other one. So here I should be a little bit technical. So I should define what is a labeled graph. So or boundary graphs. So boundary graphs are the graphs. I have a graph. It's a normal graph, and then I pick up a subset of vertices, and I put labels on this. So this is a boundary graph. So the labeled set of labeled vertices is called the boundary of the graph. And if I have two boundary graphs, I'm able to define a kind of gluing operations on these boundary graphs. So I take two boundary graphs and I identify vertices with the same labels. Right? And I don't care so much about ages. So just yes, if there is if there are some, and also I add ages which are missing, say, in between labels in one graph or the other graph. This is what I do. This is a labeling operation. And then for labeled graphs, I can define what is a finite integer index for graphs. And this was defined quite a long time ago already by Badlander and Van Antwerpen de Vleutier. Well, it's probably the correct spelling. And yes, so what is a finite integer index? So parameterized problem has a finite integer index in a graph class G if for every integer t there exists a finite set of t boundaried graphs such that this is a subset of the set G, and then for any t boundary graph of G1 there exists a graph G2 from the set, such that if I replace this graph by the graph G1, such that if I take the graph G1 and replace it by the graph G2 from the set, the result will be the same. Right? So this is a kind of equivalence relation.
So G2 depends on G1?
What do you mean?
I can look at G1 and decide one G2, or I can look at some other G1 and decide.
No, but this set is so basically it depends only on the class, right? So you give it's yes, and there are a lot of problems with finite integer index. So if you start, so the finite, so yes, this is just I don't want to read all these problems, but there are quite many problems, and many natural problems which have this property. So the problem also another with finite integer index that it's not always easy to understand or to prove that your problem has a finite integer index. Sometimes it's clear, sometimes it requires some work. But there are a lot of this type of problems. Yes. And now I can say a bit more precisely, so why protrusions work. So basically, what's happening? So if I have a problem which has a finite integer index, and then and if I have a protrusion in the graph, right? So then I'm always able to replace this protrusion or this graph with equivalent instance. And the equivalence instance looks exactly the same as this graph, except this part of the protrusion. And the protrusion is replaced by a protrusion of smaller size. This is why protrusion works. So if you have questions, maybe we should make a small break. Just please ask, because we will go further. All these things. Okay, so this is the main notion. So what we are doing, and so then the remaining part of the talk will be what we are doing. So if I have a problem and I want to prove that this problem has a polynomial or a linear kernel, so what I want to prove is, first of course, I have to show that the problem has a finite integer index. But yes, and the second problem, and the second thing which I have to establish to prove that the problem has a polynomial kernel, I should prove that large yes instance of the problem has protrusion. I should make a photograph of the audience sleeping. Just that's well, that's fine. That's fine. There was a difficult flight, so that's yes. So I would not speak much about how to show that the problem has a finite integer index. So that's another story. It's also an interesting change. Well, for most of the problems, we know how to prove things, but also sometimes it requires some ideas. So it's a bit harder to prove things that a problem has a finite integer index. For example, that proving that problem is expressible in monadic scalar logic, for example. So this requires some additional work sometimes. But what I will talk to today is just I will give you several examples showing that what kind of combinatorics you have to use to obtain to prove that your problem has a large protrusion. And then so this requires some nice combinatorics usually here. Yes, and so the first part is on the property which is called quasi-compactness. And quasi-compactness and why many problems on planar graph have linear kernel. Well, so the story goes back to the very nice paper of Albert, Fellow, and Niedermeyer. That's in the journal of ACM 2004. And in this paper, they proved that K dominating set on planar graphs has a linear kernel. And basically, the proof, or the idea of the proof, well, it's a quite simplification of the idea of the proof, but basically what they prove, or the idea was, that they are able to separate, or to partition, so you have a planar graph, right? And they were able to partition this planar graph in big O of K regions. And then for each of the region, they were able to apply some reduction rules, such that the size or the amount of vertices in every region becomes a constant. So you have big O of K regions of a planar graph, and every region contains constant number of vertices, which means that the size of the reduced graph is also a linear function of K, big O of K. That's the main of the idea. So basically, what is the region in this understanding of Albert, Fellows, and Niedermeyer? So the region is just a kind of, so you have a planar graph, and then you have some it's real regions of the plane. So there are some paths in a graph which partition the plane into regions. And the properties of these regions were that every region has a constant number of vertices on the border, and also of constant diameter. If you know how trees works for planar graphs, if I tell you that I have a planar graph of a bounded diameter, you immediately say, this planar graph has a constant trivets, right? That's one thing. But then, which also already smells a little bit like protrusion, right? So what Albert, Fellow, and Niedermeyer were doing, okay, they had this region decomposition. And then for each region decomposition, they used data reduction rules. So, and there's a quite extensive case analysis there. So basically what they were doing, well, there are some kind of intuitive reductions. For example, what they do in this reduction rule, if I have two vertices, V and W, right? And then I look at the neighborhood of the guys. If there is many vertices adjacent to V and W, and which are completely dominated by these two guys, it doesn't make sense to keep all these vertices in the dominating set, right? Because anyhow, not all of them will go there. So I'm able to remove some of the vertices. I'm able to reduce my instance. So this, for example, there's examples of another reduction rules. So, and there are several more rules in this paper, but this is just to give a flavor or intuition how things work, right? I partition my graph, and then in my graph I start arguing for dominating set, which vertices I can remove, maybe which vertices I cannot remove, and if I cannot remove some vertex, I should maybe label this vertex to say that this vertex should go to dominating set, etc., etc., etc. But, and then also it appears that that was a very influential paper, and it appears that many problems on planar graphs have a linear or a polynomial kernel. And there was a lot of papers in this area from 2004. And people were doing different problems on planar graphs, and basically, the problem is that why almost every problem requires a separate paper, because basically the ideas were quite the same. So you take a region decomposition of the graph, but then how to describe the reduction rules. For each problem, you should have probably different reduction rules. And that was the main, difficulty. So that was, yeah, that deserves to be published somehow, right? So because you find the new rules, you reduce the problem. Sometimes it's very non-trivial, also things. And also there was a kind of general framework which was suggested by Guo and Niedermeyer. So basically what they obtain, they show that for many problems you have a so-called region decomposition. So again, region decomposition is you are able to partition your plane into regions such that the boundary of the region is of constant size. And so the region decomposition is just I cover the whole graph with these regions, and the intersection of the graph intersects the decompositions only in the boundary. And also the property of these things is that every region is separated by a constant number of vertices, so the boundary of the region is constant, and also every region is of constant trivets. Does it ring any bell already? No? Just let's come back to the definition of protrusion, right? So I define protrusion as a graph of constant trivets, which communicates to the outside world through a small constant separator. This is exactly the protrusion, right? Because why? So these guys are separated from the remaining graph by a constant number of vertices. And also the diameter here is constant, so it's constant trivets. So this is exactly the object we are looking for. Okay, so this is just for free. This is a protrusion. And for free, we get that all problems with having a finite integer index, and all problems which have a region decomposition, they have linear kernel. This goes almost for free for us, right? You realize. Okay, then the question is, are we able to describe what kind of problems have a region decomposition? That's the first question. And the second question is, okay, so if things work so nicely for planar graphs, maybe they can work for other types of graphs as well, right? So it's yes, and then the first result I want to explain is the result. So we show how or what kind of properties in the graph they really implies the region decompositions. So and this is the notion of quasi-compactness. So I say that parameterized problem is quasi-compact if there is some integer such that if I take my problem on planar graphs, I can take at most, so I can take the set of vertices as of size at most r times the parameter, r times k, such that if I remove these vertices and also bolts around these vertices of constant radius, my graph will have a constant trivets. What do I mean by ball? So ball here is in the metric, it's called a phase, vertex phase distance. So basically it's the distance, if I have a vertex in a graph, then the distance is I go to the neighboring phase, and then I go to the neighboring vertex, neighboring phase. So this is the distance in my planar graph. So once again, so what means quasi-compactness? So basically, I just can remove a constant amount or linear amount of balls of constant size, and what remains is of constant trivets. So why we call it quasi-compactness? Because first we introduced the property which we call compactness, which means that I just able to remove at most k vertices, or just I'm able to remove linear amount of vertices to make my graph of. No, sorry. I'm able to remove at most so linear amount of balls to cover the whole graph. So it means that I have just kind of finite cover. So it's a compactness property. But then we realize also that so basically even what remains is not covered, but is of constant trivets, it's still fine, and things can work for that. Right? So for example, so what will be the problem which is quasi-compact, for example, it's a feedback vertex set. So feedback vertex set, the problem is I want to remove at most k vertices such that my graph is acyclic, or of trivets 1. Right? This is a clearly quasi-compact problem, right? Not only for planar graphs, but I remove at most k vertices, and what remains is of constant trivets. Just try to think of it this way, right? So once again, so the quasi-compactness property, planar graph, and maybe of huge trivets, but this the huge trivets is or non-constant trivets is around just some balls of the vertices. So that's yes. And then so what is possible to prove that quasi-compactness on planar graphs yields existence of large protrusions in yes instances of large size. This requires some work. It's not completely trivial, but as far as we have this combinatorial result, immediately what we have the first meta-algorithmic results, because if we have a quasi-compactness and finite integer index, it means that we have a big protrusion. It means that we have a linear kernel in a graph. So that's and also with much harder work, it's possible to extend this result to graphs of bounded genus. And basically, yes, why it's become messy for bounded genus is, well, so the matrix also changes. So what is the phase vertex distance in bounded genus? That requires some understanding. And also then we have to do inductive cuts to reduce the genus of the graph. So things still can be pushed through. So as a corollary, we have that, well, there are a lot of problems which have a finite integer index and which are quasi-compact. So that's like dominating set, also the extension of R domination, so the dominating at some distance at most R, vertex cover connected dominating sets, and many different and traversals, packing, covering problems. So, but okay, so I also promised to speak about bidimensionality. So, and actually, bidimensionality appears to be a very handy tool also to prove kernelization. So what is, well, I should explain what is bidimensionality. So maybe I should start from a definition of minor. So what is a minor? If I have a graph, I can define basic operations on the graph. So basic operations are vertex removal, H removal, or H contraction. Right? 3 basic operations. And then I can define that one graph is a contraction of the other graph if I can obtain graph from the other by a sequence of H contractions. Or a graph is a minor if I can obtain one graph from the other by a sequence of contractions, vertex removal, and H removals. Right? And it's a kind of folklore which says that it doesn't matter which operations or in which order you do these operations. And it's quite easy to see that it doesn't matter. So the notion of minor. And then I say that the parameter is P is minor bidimensional. So I have some parameter on graphs. If for any pair of graphs, if one graph is the minor of the other, it means that with this parameter k, if I have if g of k is the yes instance of my parameterized problem, then the pair h of k is also yes instance. So taking a minor operation doesn't grow my parameter. So and the second thing is that if I take a look how my parameter behaves on a planar grid, which is a path times path, right? This is a Cartesian products of 2 paths. Then if k is smaller than some delta squared, or I should say it this way. So if the parameter is significantly smaller than amount of vertices in the grid, then this is a no instance. So the value of my parameter on the grid should be of order the number of vertices of this grid. This is the second condition. So minor closeness condition, and second, my parameter should be large on the grid. And this notion, it was developed basically to get sub-exponential fixed parameter tractable algorithms on planar graphs. But then it appears also that this notion become quite also handy, for example, for obtaining polynomial time approximation schemes and even efficient polynomial time approximation schemes on planar graphs and also on graphs of bounded genus and all these things. And also why I say it's handy, because also it's also quite simple criteria. So for example, for obtaining sub-exponential time algorithms, it's very easy to say if your problem has a sub-exponential time algorithm just by making use of bidimensionality. This is one thing why it was useful. And the second thing is also by making use of bidimensionality, it's very easy to go from planar graphs to much more general classes of graphs, like graphs of bounded genus or a graphs excluding some constant fixed graph as a minor. So this is just so this machinery is very useful for this type of things. And the same also for ptases. So by making use of bidimensionality, it's possible to extend many results for planar graphs to larger classes of graphs, and also for many new problems as well. So of course it was natural that we try to also to play to see if you can use bidimensionality for kernelization. But unfortunately, bidimensionality doesn't work directly for kernelization, but also as for ptases, we need some additional constraint on the problems. So in this constraint called separation property. So I have if I have a minor bidimensional problem, I say that the problem has a separation property. If for any vertex cut S, I take an optimum solution in a graph, and then I take any union of components which I obtain after removal of the set S, and then the solution of my problem on these components would not much different from the solution from the intersection of the optimum solution to these components. So maybe in human language to say these things is, so what is the separation property? I have a problem and I take a separator. When I remove the separator, I have several components. I take a look at the optimal solution on each of the components plus this separator. And I compare what I obtain, the new solution. I compare with the intersection of my previous solution with this component. And if these things do not differ much, then I say that this is a separation property. Right, so basically it's well, I didn't give an example here. For example, why vertex cover has a separation property, right? If I take a solution, optimal solution for vertex cover on my graph, I take a separator, and I solve optimally the vertex cover on each of the components. Then if I just add all the separators to the vertex cover, the solution which I obtain for vertex cover in each of the components it's not much different from the solution which I get so optimal solution in the original graph, which is intersecting these components. So it doesn't change much, the separation. Of course, it changed the solution, but the solution, the global solution, it really depends nicely on the solutions in the components. Yes. And then, so the following theorem was proved in 2010 that if I have a minor bidimensional problem which has separation properties on H minor free graphs, then I have a large protrusion of large size. That's again, so that this goes to kernelization. And basically, the proof of this result is based on the following observation. Suppose I have a set of vertices of size at most k. And then, so if I have a H minor free graph, so this is my parameter, so I'm looking for this is a solution for my problem. So if the tree is, and I know that if my graph is H minor free, and because of bidimensionality, it's possible to prove that the tree width of my graph is something like the big O square root of k. Yes, and then it means that I'm able to find a separator in a graph, a balanced separator, of size square root of k, which separates the solution in a balanced way. And the size of the square root of k is the parameter. Okay, and then as to what we start to do, we start playing with this type of separators. So if you find the right way to separate the set S, and you start to play with the property of the sublinear separators, then and you apply this argument recursively, it's possible to prove that every graph, for every graph, it's possible to remove a set of vertices y, which is of linear size of k, with the following properties: that the tree width, that the amount of neighbors of this component is always bounded by a constant, and the other thing is that the amount of vertices of the solution in my graph, which are in this component, is also constant. This is kind of applying these recursive arguments. But since now I start using bidimensionality again, I know that if I have a constant amount of vertices in my graph from the solution, it means that the tree width of the graph is also constant. Right? It's using again bidimensionality, which means that I have a protrusion. It's communicate to the outer world via constant amount of vertices. The tree width is also constant, right? We are happy, right? We have protrusion, we have kernel, we have everything. So minor bidimensionality, minor bidimensionality plus separability on H-free graphs yields existence of large existence of large protrusion and yes instances, which means that we have kernels. So many problems which have these properties have linear kernels on H-free graphs. Yes, and then also there is a notion for bidimensionality for contraction closed parameters. So basically, the most important problem for contraction closed problems is dominating set, right? Because dominating set is not minor closed. Because if I remove edges, I can increase dominating set, right? But the dominating set is closed under operation of taking contraction of edges. So it means that contraction closed, it's also possible to define contraction bidimensionality. It's also possible to extend these results to contraction closed parameters up to some extent. Okay, so far what I was telling, all these protrusions, they work for graphs which has kind of topological properties. Either I can embed a graph on a surface or on a sphere, or there's still something very sparse. And in the conclusion of my talk, I also want to speak a little bit on more general things, more general graphs. And for more general graphs, we try to solve the following problem. So it's a F deletion problem. So what the problem is about? I have a graph G, and I have a parameter K. And then the question is, can I remove at most K vertices such that remaining part of my graph doesn't contain a graph from the set F as a minor? Right, so I just want to, yes, I have a graph, and I want to remove I want to hit all graph minus by removing at most K vertices in the forbidden sets. So for example, so just to be, so what is this hitting set, basically? Well, if I have vertex cover is a F deletion problem, right? Because what I'm doing for vertex cover, I want to find a set which hits every edge, which means that my remaining graph, when I remove all the K vertices, is independent set. Which means that independent set, it doesn't contain there's no edge in the remaining graph, right? So if I take, say, my forbidden set of minus is K2, this is just F deletion problem, is just vertex cover. If I go a little bit further, so a feedback vertex set, I want to remove K vertices such that my graph is acyclic, which means the graph is acyclic, it doesn't contain a cycle, right? And it doesn't contain a cycle, which means it doesn't contain a triangle as a minor. So this is, if I take this set to be equal to C3, I have a feedback vertex set. Let's go further, right? For example, if I want to remove vertices such that my remaining graph is planar, this is Kuratowski-Pantragen theorem, saying that planar deletion set so no planar graph contains K33 and K5 as a minor. So for example, I can express this problem in this way. And say if I want to remove vertices to get out of planar graph, this is, so you got the pattern, right? So there are a lot of things which I can express in terms of forbidden minus, many problems. I just remove vertices and I get this problem. So path it's one deletion set, also for example, is of this type, right? So I can express graphs of path it's one with two forbidden minus. And then I have kernelization, or this is the P diamond hitting set. This is a diamond, two vertices connected by three paths. And then I just want to hit, yes. Then it's the forbidden graph is theta 3. This is graph theta 3. Yes, so what we know about this type of problem? So by Robertson and Seymour theorem, right? If I have a F deletion problem, this problem is expressible, every instance, instance of the problem is expressible by a finite set of forbidden minus. And then by Robertson-Seymour theorem, I am able to, all these problems are fixed parameter tractable. Right? But yes, so yes, all of these problems have a kernel. But also, I start in the beginning of the talk giving examples for that there's a polynomial kernel for vertex cover and for feedback vertex set. So the question which seems to be natural here, is there a polynomial kernel for every set F? or not. And this is still an open question, but what we are able to prove is the following result. So if I have a set F which contains as abstraction a planar graph, then this PF parameterized F deletion problems admits a linear vertex kernel on graphs excluding this star, K1T, as a new subgraph, where this is some fixed integer. So for example, this class of graphs contains graphs of bounded degree, right? Because, well, if my graph is of bounded degree, I cannot have this induced star as a subgraph. This, say, line graphs are the famous example. So claw-free graphs, line graphs are claw-free graphs. Or, for example, another example, unit disk graphs. It's known that any unit disk graph, the graph which is intersection graph of unit disks on the plane, it doesn't contain also this K17 star as an induced subgraph. And the other theorem is also, this is for general graphs, that if our abstraction contains this theta C graph, so the C is the amount of edges going from one vertex to another, then this deletion problem has a kernel of size k square log polylog k. And again, so it means that, again, this solves the problem vertex cover, because vertex cover is the example of this F deletion problem with theta with C equal to 1, right? I just want to exclude all graphs I want to exclude all edges. Feedback vertex set is also another example of this type of problems, is expression of this problem for C equal to 2, or a diamond heating set is for C equal to 3, right? So it's, again, this is a theorem for a class of problems. Even this graph looks like a quite simple graph. It also includes many known problems as a sub-problems. So this is and the proof, again, surprisingly, is based on protrusions. So basically what we are able, and this is the main combinatorial lemma, so which basically provides all the results for the problem, is the following. So if I have an n-vertex graph, and I have some set of vertices, such that removal of the set of vertices brings me to the constant trivets, then I have a protrusion of this size. No, sorry, I have a protrusion. This is the trivets and the body of the protrusion, and the size of the protrusion is of this way, for some constant d. And as far as we're able to obtain this result, we already have the hammer, and we already start to playing with the things and proving the results. Yes, and yes, this is for the proof of the first theorem, and for the second theorem there is much work actually to be done. But again, so the main idea, if we are able to bound degree or vertex degree of the graph, then we can start using the protrusions here. So that's a requirement. Yes, to conclude. So what we discussed in these talks. Yes, so there were several given, generic or meta-algorithmic results for kernelization, how to obtain kernelizations. And I hope I convinced you a little bit that protrusion is a quite nice tool for this kernelization results. So every time when we have this, our kernel, we use protrusion. That was the main tool. And the other thing which is also what I want to mention, that this finite integer index, it's a bit strange property. For many results, if we can replace it with a monadic second-order logic, but then so we don't have linear kernels. So it's and still I'm not completely sure. So maybe it's possible to replace it. It will be also quite nice actually to replace. First, in our theorems, if you want to get linear kernel, to replace finite integer index with either by monadic logic or by counting monadic logic or some variance. That's a bit more general result. But this we don't know, and this is kind of open. And just to conclude with a very concrete, conjectures or assumptions. So there are two conjectures. So, which I believe are the following things. So, if I have the first conjecture is if I have an abstraction set F, which containing a planar graph, then this problem admits a polynomial kernel. So far, what we are able to prove, we were able to prove that only if the set is this theta C graph. But somehow it seems that this thing should work for any planar graph. This is one thing. And the other thing, which is also, well, at least it will be nice to believe in these things. So maybe that there is a kind of real dichotomy in this case. And the real dichotomy, I think, is here. So when the set F contains non-planar graph, say K5, there is no polynomial kernel for F deletion problem. And why I think so? Because at least all our arguments, they file apart immediately. So as far as we exclude this graph as a minor, there's no bounded tree width, there's no protrusions, everything just, I think, well, yes. Even if you are able to prove this thing with our tools, this thing will be impossible to prove. Just you need some new techniques. And this is why I believe that most likely this should be true. Yes, that's the end of the talk. Thank you very much.
Are there any questions?
Are there any hammers for proving that a problem admits a finite integer index? Like, is there is some implication between MSO expressibility?
Yeah. It's also in our paper. So basically, what you need to prove. So what we are able to prove that if you have a monadistic logic plus condition which we call monotonicity, so it basically say that your problem doesn't depend so much what you do on the bottom of the problem, then it has finite integer index. But it's we're not sure if it's if and only if. Most likely not. So it's but this is some condition for that.
Any more question? Okay, then let's thank the speaker again.
So welcome to the first session of APEC. So the first talk will be on are there any good digraph width measures by Somnath Sitkar. So please.
Thank you, Yngve. So this is joint work with a number of people from two groups, theoretical computer science at RWTH Aachen University and Faculty of Informatics at Masaryk University in the Czech Republic. And Robert Gagnon, Jan Obrezalek are in the audience along with Peter Rossmann. The others are not here. Okay, so I'll be talking about are there any good digraph width measures. Just let's look at a motivation for width measures. What we know about undirected width measures. We know this is we all know about tree width. It's extremely successful. And why is it successful? Because, well, you can solve a lot of problems in linear time on graphs of bounded tree width. And you have nice closure properties. And you also have this, if graphs of small tree width have a sufficient rich structure. So they're nice. Small tree width graphs are also nice to look at. Along with tree width, you have these other width measures, new width measures, clique width and rank width. And they also share this property with tree width that you can solve a large class of problems in either FPT or XP time. In this case, in case of rank width and clique width, it's MSO1. But in case of tree width, this is the whole of MSO. Okay, so for undirected graphs, you have a few good width measures. Good in the sense that they admit efficient algorithms for a large class of problems. Now, if you look at the directed graph scenario, this kind of changes because you have lots of width measures, and there was firstly an attempt that really plays a part of tree width. Okay, so what are these width measures? You have some of these width measures are game-based width measures, DAG width, Kerry width, DAG depth. There are other measures. Kenny width, for instance, counts a number of distinct die paths between two vertices. The cycle rank, which originated in the 1960s, it talks about the nesting structure of cycles, the DFVS number, the distance from being a cyclic. Directed clique width is based on K expressions, and bi-rank width is just an extension of the undirected rank width for directed graphs. Now, if you look at the structural properties of these width measures, what we find is that these width measures, DAG width, Kerry width, and DAG depth, the ones that are based on this the cops and robber game characterizations, they have good closure properties. So they're monotone undertaking subgraphs and some restricted form of arc contractions. Directed tree width and these measures, they don't have a game theoretic characterization, but they're monotone undertaking subgraphs. And if you look at these with two width measures, directed clique with birank width, they're not monotone undertaking subgraphs, but they are monotone undertaking the so-called vertex minor. So, okay. So if you look at, so these are the structural properties, essentially the closure properties of width measures. If you look at algorithmic usefulness, and that is how large a class of problems can they solve on graphs of bounded width, and we find that the width measures which did not have good closure properties are really successful, because for directed clique width and birank width, they solve all of MSO1 in FPT time, and many other problems which are not in MSO1 can solve in XP time. So here is this empirical evidence that for directed graphs, width measures that are algorithmically useful, in the sense that you can solve a large class of problems, a large framework of problems on graphs of bounded width, don't seem to have good structural properties. And this is something we try to formalize on this talk. Right. So let's try to formalize some of the, for this, yeah. Okay, so let's suppose you are designing a digraph width measure, and what are the features that you would probably think about? One, of course, is this algorithmic usefulness. You can solve lots of problems on digraphs of small width. Secondly, for directed graphs, you want the width measure to be different from tree width. And otherwise, you could simply use the tree width of the underlying undirected graph. Okay? And thirdly, you might want the width measure to have nice structural characterization. It's nice closure properties. It's not a necessity, but I mean, this is what you might think of as one of the properties if you're designing a new width measure. So what we're going to show is that there is no width measure that satisfies all these three properties. So we need to formalize, of course, what we mean by algorithmic usefulness, being different from tree width, and having nice structural properties. So this is what we're going to do next. Right. So what is algorithmic usefulness? So we define a width measure to be useful or powerful if you can solve all problems in MSO1 in XP time. So in time that is, size of the input measure to some function of the width measure. So the width is a parameter, and so why we use MSO1? Because this is what we believe. If you're designing a new width measure, you should be able to solve a whole framework of problems, not just some problems here and there. And if you want to capture a whole framework of problems, it's natural to look at logic-based frameworks, and then you should be able to talk about vertex sets or edge sets. And then MSO1 is just the least common denominator. Okay. So we require. So when we say a width measure, so for us, algorithmic usefulness is the ability to solve all MSO1 problems in XP time. Right. So our second condition was being different from tree width, and for this, let's try to define what we mean by tree width bounding. So we say that a width measure is tree width bounding if bounded directed width implies bounded undirected tree width. So if you have a digraph so you have this width measure delta, if the delta width of a digraph is bounded, look at the underlying undirected graph, that's going to have bounded tree width. Okay. So what we want, so the definition of different from tree width is we don't want the width measure to be tree width bounding, which means that there is a class of digraphs of constant width whose undirected counterparts would have arbitrarily high tree width. Okay, so this is what we mean by being different from tree width. Okay, and our third condition would then be what do we mean by nice structural properties? Now, if you look at the width measures that are based on cops and robber games, one of the observations is that if you shrink a path, an induced 2 path, then that does not help the robber. Okay? So if k cops can catch a robber in a graph, and if you shrink a 2 path, an induced 2 path in the graph, k cops will continue to catch that robber. So it just seems that if you want a width measure that is based on a cops and robber games characterization, then shrinking induced 2 paths should not help at all. Which means that width measures based on cops and robber games should be closed under some form of topological minors. Okay, so this is not, we're just trying to formalize, there is no notion of, or formal notion of what a cops and robber games, robber game based width measure is, but this is our formalization of this notion. Okay? So we formalize this as a width measure is cops and robber games based if it's closed under directed topological minors. I'll define what this is. So topological minor is for you of an undirected graph. You have an undirected graph G, and you obtain a subgraph of G, and you shrink induced 2 paths. What you get is a topological minor. You do the same thing for directed graphs. So a graph H is a direct topological minor of a digraph T if H can be obtained as follows. You take a subgraph, subdigraph of T, contract certain arcs, and you obtain H. Of course, for directed graphs, you have to be careful about which arcs you contract. And our position is that we allow arc contractions. You allow an arc to be contracted if it does not create new die paths between large degree vertices. Okay? And why large degree vertices? The intuition is that you can create new die paths between 2 small degree vertices. If you have a long 2 path and an induced 2 path in the undirected sense, the arcs can be oriented all sorts of ways. But if you contract an arc and if you have a new path between 2 degree 2 vertices, and that does not really change the topological structure of the graph. Okay? And it does not help the robber also. If there is a new path on an induced 2 path. But you don't want a new path to be created, new die path to be created between vertices of large degree. So we prohibit that. So this is our definition of contractible arcs. V3 is the set of vertices with at least 3 neighbors. Then you define an arc to be contractible if not both endpoints of this arc are in V3, and contracting this arc does not create new die paths between vertices of V3. So our definition of directed topological minor is as follows. You obtain a subgraph, and you contract arcs of this type. The digraph that you obtain is a directed topological minor of the original graph. Okay. So we have 2 versions of our main theorem because the version that we have in our paper is slightly weaker. Last week we found a stronger version. So let me first state the version that appears in the proceedings. So for this version, we need another property, another technical requirement, which we call efficient orientability. So intuitively, a width measure is efficiently orientable if you can do the following. I give you an undirected graph, or you give me an undirected graph. I can somehow orient the edges of the graph in polynomial time such that the resulting digraph has optimal directed width, and the optimal being computed over all possible orientations of the undirected graph that you've given me. Okay? Now, so this is not such an arbitrary requirement. If you look at, say, directed clique width or birank width, if you give me an undirected graph, I give you a symmetric orientation of that undirected graph, and that digraph will have minimum birank width or minimum directed clique width among all possible orientations of the undirected graph that you give me. For DAG width, for instance, and Kelly width, if you give me an undirected graph, I simply orient the edges of the graph so as to obtain a DAG, and that's going to give me minimum DAG width. Okay? So I can do this in polynomial time. So the idea is that you give me an undirected graph, and I just have polynomial time, orient the edges somehow to get optimal. Actually, we don't need optimal, so suboptimal will do. Okay. So the statement of main theorem is as follows. If you have a directed width measure that is powerful, which means that you can solve all of MSO1 in xp time, and in addition satisfies the following three properties. It's not tree-width bounding, and it's closed undertaking directed topologic minors, and it's efficiently orientable, then we can show that P equals NP. So it's just a reduction from some NP hard problem. And what we observed was that you can actually, the proof actually goes through if you make the following assumption: delta is just not efficiently orientable. So here we assume that delta is efficiently orientable on all undirected graphs. So I mean, the definition of efficient orientability is that given any undirected graph, I can give you an orientation of the graph with near optimal width, directed width. But what we just need is the delta be efficiently orientable on some fixed subdivision of the cubic grid. So we don't need the efficient orientability on an arbitrary class of graphs, we need it on a fixed class of graphs. And for a fixed n, this orientation, the optimal orientation of the edges, can be supplied as an advice string of length polynomial in n. Okay. With this observation, we just have, instead of P naught equal to NP, we have, so if you have the orientation and all the other width measure, other properties, if it's powerful, delta is powerful, and delta is not tree-width bounding, delta is closed undertaking topological minors, and then you can solve this NP-complete problem in polynomial time with polynomial advice. So you've shown that NP is contained in P/poly, and because this implies that PH collapses to the third level, so you can just say that the existence of such a width measure implies that the polynomial hierarchy collapses to the third level. Okay, so this is our strengthening, which is of our main theorem, which is not there in the proceedings. Yes. So we just saw that we can take away efficient orientability, and we have a strengthening of result. Can we strengthen the result even further? So in particular, can we strengthen the result by demanding closure under subdigraphs instead of directed topological minors? And this doesn't seem to be true because we show the existence of an artificial width measure which satisfies all these properties. It's not tree-width bounding, it's closed undertaking subdigraphs, it's powerful. In fact, in this, the delta that we construct is also efficiently orientable. So it doesn't seem that you can strengthen the result any further. Okay, so the main result is if you're designing a digraph width measure that is different from tree width, and you want it to be useful, don't expect it to have a Robert and Kopf-Scheme characterization. It just won't work. So, and okay, so with respect to being powerful, we have a threshold. So if it's monotone under directed topological minors, you don't have, it's not powerful unless NP is contained in P/poly, but if you require monotone under subgraphs, we have a width measure that is powerful. So, and this requirement under closure under direct topological minors, we think this is a good necessary condition in any definition of Kopf and Robert games based width measure. So if you want to formalize what this means, this just might be a good thing to put in. Thank you.
Any questions? So I won. I was wondering, this.
In talking about your presentation, the one that Rick mentioned is the definition of how it is powerful.
Yeah.
Why is MSO the right one for direct?
Well, as such, there is no logical framework, no well-known logical framework for directed graphs. So the undirected MSO, because you can talk about vertex sets, it seems like the right candidate. But there is no natural framework specifically meant for directed graphs. So
Yeah, look at the thing is the MSO in some sense, because
it does.
is inherently symmetric, so it has access to the underlying undirected.
Yeah, so it ignores direction somehow. So yes, we have considered this. So we're trying to look at some natural framework for directed graphs, some logical framework which would just take the orientation into account and not just look at the underlying undirectedness. Yeah. This is still work in progress.
Okay, other questions? So I was just wondering what problem you reduced from.
Oh, it's so basically it's a problem on a class of planar graphs called 1-3 planar graphs. So planar graphs of degree at most 3. So what we show is that there is a very large class for every problem on that's NP hard on undirected graphs. There is an interpretation of the problem that is hard for this very restricted class of planar graphs. Okay. So there are lots of problems that are NP complete on just 1-3 planar graphs, and in particular we have one fixed problem which is called fair 4 coloring, which is NP complete on planar graphs in 1-3 planar graphs. And yeah, this is the problem that we used from. So basically, if the width measure is not tree width bounding, for constant delta width, you have an unbounded tree width. An unbounded tree width is going to give you large grid minors, a large cubic grid minors. And you can obtain 1-3 planar graphs as minors of the graph. But because these are 1-3 planar graphs, they have the degree upper bounded by 3. They're not just minors, they're also topological minors, not just in the undirected sense, but also. So there is some orientation of some subdivision of a 1-3 planar graph that would have small delta width. But then we assume that the delta width is also closed under directed topological minors. So you can actually shrink these two parts. So you can have, what we argue is you have a small subdivision, an orientation of some small subdivision of 1-3 planar graphs that have constant delta width. Okay. So now, if you start with an NP complete problem on 1-3 planar graphs, and if you assume that your width measure is powerful, so then you can solve this interpretation of this NP hard problem on this fixed subdivision of this 1-3 planar graph in polynomial time, because you assume that you can solve all of MSO1 in XP time, because width is constant. This argument just shows that there is an orientation of some fixed subdivision of a 1-3 planar graph with small delta width. And then the XP algorithm would just mean a polytime algorithm in this case.
Other questions? Okay, otherwise we thank the speaker. So, second speaker of the session is Michael Philipsou. If I pronounce it reasonably correct. And he will go on to talk about deleting vertices to get to pathway 1.
Okay, thank you. At first I would like to thank the organizer for inviting me here to talk to you about an improved FPT algorithm and quadratic kernel for path with 1 vertex deletion. At first I would like to say that this is a joint work of our Warsaw team, Marek Cygan, Marcin Pilipczuk, and Jakub Onufry-Wojtaszczyk. Okay, so what's the problem? In this path with 1 vertex deletion problem, you are given a graph, G, a simple undirected graph, and an integer k, which is also a parameter. And you are asked whether you can delete at most k vertices of the graph in order to get a graph with path width at most 1. Okay, so the study of parameterized complexity of this problem has been initiated by Philippe Roman and Villanger in their WG paper this year. And the results they have obtained is O star of 7 to the power of k FPT algorithm, which is rather a simple algorithm, and a quartic kernel. So we pushed down those results into 4.65 to the power of k FPT algorithm, which is a quite a big improvement. And the major part of the paper, a quadratic kernel for the same problem. Okay, so let us take a closer look on the problem. So we would like to obtain a graph of path width at most 1. So as I think Fedor noted it and Mike follows as well, that graphs of path width at most 1 can be very easily characterized. So the graph have path width at most 1 if and only if it is a forest, yeah, because all the cycles have path width 2. And it does not contain as a subgraph as a graph T2, which looks like this, namely a T, but with all legs of length 2. Okay, so we would like to delete k vertices at most from the graph in order to kill all the cycles, yeah, and kill all the T2s. Okay, so such a graph that have path width at most 1 are called a forest of caterpillars, where a caterpillar is such a graph, a path with possible pendant vertices attached to it. And you can easily show that that graphs that suffice those two conditions are exactly disjoint sums of those caterpillars. So we would like to delete at most k vertices in order to obtain a disjoint sum of caterpillars. Okay, so to get familiar, consider such a graph and observe that this is a fuzable solution because we end up with a caterpillar with one pendant here, yes? However, this is not a solution because we have here a T2, yes? And this is not a solution as well because we end up with a cycle. Yeah. Okay, so in the first part of the talk, I will talk about the 4.65 FPT algorithm, which is rather simple but tricky in a way. Okay. So at first, I would like to show you some idea what was the main idea of this previous best algorithm, this O star of 7 to the k algorithm. So we branch out over all cycles of length at most 4. We must kill them, so we just branch which vertex from all the cycles of length at most 4 we take. This is branch into at most 4 instances. And we also branch over all T2s. Note that a T2 has 7 vertices, so we branch out into 7 instances. And we observe that if the branching cannot be applied, we can have also only larger cycles. And you can easily show that such a graph is a disjoint sum of caterpillars and somehow cyclic caterpillars. That means a simple cycle with possible pendants attached. And this instance is already can be solved in polynomial time because for each cyclic caterpillar you have to use at least one vertex, and you can use at most one vertex. You just break the cycle by deleting one vertex. Okay, so our idea was that the branching over those T2s, which is the most expensive one, can be done in a smarter way. Okay. So what was this previous algorithm doing? Assume that we've already branched over all cycles of length at most 4. So the idea was that either this vertex is in the solution, or this, or this, or this, or this, or this, or this. 7 branches. Yeah. But observe that it can be quite uncommon in the graph that such a middle of the leg has degree only 2. So assume that the picture looks like this, that those midpoints of the legs have also some other neighbor, and their degree is at least 3. Observe that as with branches over all cycles of length at most 4, the picture is just like this, because meaning that this vertex is not the same as this vertex, because otherwise we would have a cycle of length 4. Okay, so now we branch. Either this vertex is in the solution, or this, or this, or this. Okay, so assuming we haven't found a solution yet, we can say that all those 4 vertices aren't in any solution because we've done the branch exhaustively. So now observe what we must do in order to kill all the T2s in the picture. If we take at most 1 vertex from this pair, at most 1 vertex from this pair, or at most 1 vertex from this pair, then there will be a left T2. So we can branch into taking both these vertices, both these, or both these. Yeah? So observe that this is a better branch because we've branched into 4 instances with parameter decreased by 1, and 3 instances with parameter decreased by 2, and this leads to a better recurrential equation. Yeah? So what about this uncommon example of legs with degree 2? So it is easy to observe that it is never sensible to take only this midpoint of this leg of degree 2 as the only one guy from the solution from this whole T2. If there exists a solution which takes only this vertex, then there exists also a solution that takes the end of this leg in which the vertex is contained. So we can delete this branch. We don't branch over this vertex because if there is a solution that takes only this vertex, it will be also found in another branch. Okay, so now if we have a T2 with 0 2-degree legs, we have 4 instances with parameter decreased by 1 and 3 with parameter decreased by 2. If you have 1 leg, we have also 4 instances with parameter decreased by 1, but only 2 with parameter decreased by 2, and so on. So we see that the most expensive branch in our algorithm is this branch, yeah, and the recurrential equation leads to exactly 4.65 to the power of k complexity. Okay, so that was sort of a warm-up because now we have the biggest part of our paper, namely the quadratic kernel for path with 1 vertex deletion. And it has many technical details, so I will treat the rest of the talk as some sort of a sketch of the proof rather than a full detailed proof. Okay, unfortunately, we will use some annotations to the edges. Namely, we will introduce a multigraph version of the problem. Namely, in this problem, you are given not a simple graph but a multigraph and an integer k, which is a parameter. And you would like to say whether you can remove at most k vertices in order to get to a forest of caterpillars. Okay, so note what is the meaning of a multiple edge. The meaning of the multiple edge is that you must take either one endpoint or the second endpoint to kill this small cycle inside. So observe that it is not sensible to have multiple edges with more than double edges. So if we have in the instance a triple edge or more, then we can reduce it to a double edge. Okay, so what about the connections between this mpoved and poved problem? So we've shown that multiple edges can always be replaced by a gadget to regain a poved instance from an mpoved instance, but the parameter increases by 1. So how will the tricky kernelization for poved go? Firstly, we will treat the poved instance as mpoved instance because mpoved is a stronger problem. Then we do quadratic kernelization for mPOVD without any tricks. Yeah, this will be a simpler kernelization. And in the end, we will replace all the multiple edges by gadgets and increase the parameter. So the parameter can increase at most by order of k square. So it is not a strong kernel or proper kernel as it's also called. Namely, the parameter can increase in the end. Okay, so what's the idea of the kernelization algorithm for mPOVD? The idea is to apply the techniques developed by Thomasin in his order of k square kernel for feedback vertex set. And the plan of the attack will be to, firstly, make a degree reduction in order to bound the degree of all vertices in the graph by some beta k for some beta. Then we will shorten long paths and tree-like protrusions in order to densify the graph. So the average degree of the graph becomes larger than 2. And in this case, the number of edges of the graph will be strictly bigger by a multiplicative constant than the number of vertices. So removing a vertex can delete at most beta k edges. So in order to delete, and we have to end up with at most number of vertices minus 1 edges, because the ending graph has to be a forest. So we have to delete gamma v edges, but each of k vertices we remove can remove at most beta k edges. So if v is larger than this number, we can immediately say no, because the counting of the edges will say that we cannot end up with a forest. And if we've bounded the number of vertices by order of k squared, then the number of edges can also be bounded by order of k squared, because we need to delete we can delete at most such a number of edges from the graph. Okay, so now we approach to the degree reduction, which we think is the most interesting part of the paper. What struck us when we read the Philip Raman and Villangar's paper is that there was a reduction that we thought was really, really strong, but it was used in a very special and narrow case. Namely, suppose that we have a vertex v, such that in the rest of the graph we have a matching of size k plus 3, such that each edge from this matching has at least one endpoint adjacent to v. Then v has to be contained in the solution, so we remove it and decrease by the parameter by 1. Why is it so? Because observe that each solution to path with one vertex deletion can kill at most k edges from the matching, so three edges won't be killed, and thus, if we don't take v to the solution, there will be a left T2 which won't be killed by the solution. Okay, so now we're ready to make a degree reduction. So assume we have a vertex v such that the neighborhood of v is of some big size, beta k, where beta is very, very large. For instance, 100. I think that 10 will suffice, but think of beta as very, very large. So I will forget some neighbors of v in order to make the situation simpler. Okay, at first I forget all the multi-neighbors, meaning the neighbors that are adjacent by multi-edges. Observe that we can say that we've forgotten at most 2k edges adjacent to v, because otherwise, if there were more than k multi-neighbors of vertex v, we could have reduced the vertex v in the same way as in the vertex cover problem. Yes, because if v wasn't in the solution, then all the multi-neighbors would have to be in the solution. Okay, so the multi-neighbors are forgotten. Now, we greedily forget edges from the rest of the neighborhood. Like, if there is an edge between two neighbors, we forget both of the endpoints. Observe that we have forgotten at most 2 times k plus 2 vertices here. Why is it so? Because otherwise, we would create here, in a greedy way, a matching of size at least k plus 3. Yes, so we would be able to reduce vertex v by this previous reduction. At the end, we forget a pendant of v, if there is any. We can always reduce the number of pendants of any vertex up to at most 1, because 2 pendants for path with 1 vertex deletion work just like 1 pendant. Okay, so now we are ready to do the main trick. Okay, so now introduce the second neighborhood of vertex v. These are the vertices that are in distance 2 from v, but they are not in the neighborhood. Okay, so we try to find a matching of size k plus 3 between those vertices and those vertices. If we succeed, then we can reduce vertex v. So assume we didn't succeed. Then by Hall's lemma, we can find a big set here x and a small set y here, such that x knows only guys from y. Yeah, they do not know those guys. What does I mean by big and small? I mean that these guys plus these guys is at most k plus 2. If you apply Hall's lemma, you will see that this is exactly the case. Okay, so see that now we can assume that this x is really big and this y is really small, because this y is bounded by k plus 2, and this x is, if beta is very large, then x can be like 10 times k. So we can apply 2 expansion lemma between y and x. So we've got a subset here, non-empty subset here, and non-empty subset here, such that each guy from here has got 2 neighbors here, has got 2 private neighbors from here, and all those guys know only these guys from the whole this set, and also from all this set. Okay, so now you can see that you can now make the reduction. The reduction is as follows. You delete those edges that were here between v and these vertices, and introduce double edges between v and those vertices. And for some technical reasons, you also must add a pendant to vertex v. Okay, I would like to argue why this graph is a simpler graph than this what we've done before. This cannot be true because the number of edges can increase in such a way, but if we apply 5 expansion lemma instead of 2 expansion lemma, everything will work. The number of edges plus the number of vertices will always decrease in such a reduction. So this reduction cannot be repeated forever. Okay, so now we approach the densification of the graph. I would like only to almost skip the slides because of the time and because it's the technical thing. So assume that the graph can be shown like something like this. Some significant vertices of degree at least 3 connected via long paths with some pendants or tree-like protrusions attached to it. We can always view the graph in such a way because we can always iteratively remove vertices of degree 1 to get this significant graph. So in the first step, we shrink the big tree protrusions here in a greedy way. And then we see that if the paths are long, if the paths are long, then there will be a big block of consecutive vertices only with pendants attached. And observe that vertices that are strictly inside such a block do not participate in any T2. So their only role is to be part of some cycle. So we can shrink the path, and if you calculate all the stuff in the Thomas M method, you will see that this suffices to apply the whole Thomas S machinery. Okay, so to conclude some remarks about further study, we think that the problem is pretty close now. Why is it? You can ask about edge deletion model instead of vertex deletion model in this problem. The problem has been already studied by Ullman and Velle under the name of two-layer planarization, and they obtained even better results. They have a linear kernel parameterized by feedback edge set, which is a stronger parameterization than just the solution size, and such a branching algorithm. Okay, as far as the kernel is concerned, the Dahlen-Melkabek's results imply that there won't be any k to the 2 minus epsilon kernel, so there will not be a significant improvement in the kernel. Hahowever, we think that the only interesting question left in this area is, can the FPT be pushed down below, strictly below O star of 4 to the power of k? Because we think that our method can be slightly improved to like 4.5 to the power of k or 4.3 to the power of k. There is much space to do it. But the really significant improvement would be pushing it below 4 to the power of k, because you would have to get rid of this branching over 4 cycles, and the whole structure collapses. Yeah, and it is also noteworthy that having an algorithm below 4 to the power of k would yield a better exact algorithm than the trivial 2 to the power of n. Yeah, and with this I would like to end. Thank you.
Any questions? Yes.
You mentioned this edge deletion variant.
Yeah.
Which is actually quite well studied. And I just want to make the remark that in his PhD, I just double checked. With Suleiman in 05 derived 3.5 to the K algorithm for the edge variant, which also has the same problems with the foresight.
Mm-hmm.
So I'm not so sure whether it could be done. So the release of reduction will probably also apply to the vertex deletion, just to make that more advanced.
Yeah, the edge deletion problem is I think it's significantly easier because, well, when you delete an edge, you delete only one edge. So you don't have to do the reduction, the degree reduction, which was the trickiest part of the algorithm. Ah, the FPT, yeah. Yeah, but I think that the edge problem is simpler than vertex problem, so it can be very hard to get below 4 here.
Okay, any other questions? Okay, let's thank the speaker again.